Stand close to a campfire on a very cold night, and you already know the rule by heart. The closer you lean in, the more the heat presses against your skin. Step back, and the warmth fades into the dark. Every fire you have ever felt obeys this. Heat moves from the hot source outward, growing weaker with distance. The surface of the sun, the bright golden layer we call its face, burns at around 5,500 degrees Celsius. That alone is hot enough to vaporize any material we have ever built. But just above that surface, in the thin glow of the atmosphere, the temperature does not fall as you move away. It leaps to 1, 2, even 3 million degrees. The outer atmosphere of the sun is roughly 200 times hotter than the surface beneath it. Heat is supposed to flow outward and weaken. Here it does the opposite. If heat simply leaked from the surface, the atmosphere should be cooler than the layer below it. This creates a glaring contradiction, as if the sun were quietly breaking the laws of thermodynamics right in front of us. We only realized the atmosphere was this hot because of a century-old mistake. For most of history, the corona was invisible, drowned out by the sun's brilliance. You had to wait for the moon to slide perfectly in front of the sun during an eclipse to see these ghostly streamers of light. During an eclipse in 1869, astronomers split that corona light into a spectrum and found a bright green line that matched nothing on Earth. They assumed nature had handed them something impossible and invented a new element to explain it, coronium. That ghost element haunted physics for 70 years. It wasn't until the 1930s that we realized the green line came from ordinary iron, but it was iron stripped of more than a dozen of its electrons, torn apart so violently that it could only glow that way at temperatures of millions of degrees. The existence of that shredded iron was the first proof that the crown of the sun was a furnace. The challenge was finding the mechanism capable of pumping that much energy from the surface into the air above it. We couldn't solve the mystery for 80 years, because the corona is 1,000,000 times dimmer than the sun's surface. It's like trying to study a candle held up beside a searchlight. Eventually, scientists realized the energy source must be the sun's magnetic field. Beneath the surface, the sun is a churning ocean of electrically charged gas called plasma, which twists magnetic field lines into a knotted, tangled mess. The physicist Eugene Parker proposed that these magnetic lines snap and reconnect, releasing violent bursts of energy. He called them nanoflares, a storm of microscopic detonations happening everywhere that together set the whole crown ablaze. But Hannes Alfvén had a different idea. He predicted that energy ripples up the magnetic lines like a shiver running down a plucked guitar string. These Alfvén waves would carry energy from the turbulent surface and dump it into the corona as heat. Both ideas were mathematically sound. However, the nanoflares were too small to see, and the twisting magnetic waves were too faint to detect. 20th century instruments simply weren't sharp enough to catch them in the act. For decades, physics had two logical suspects with clear motives, but no hard evidence to prove which one was actually responsible for the million-degree glow. To break the deadlock, we had to stop watching from a distance. In 2018, NASA launched the Parker Solar Probe to fly directly through the corona itself, the first machine built to take measurements from inside the sun's atmosphere. The probe discovered the helicity barrier. When magnetic fields overpower the pressure of the plasma, they form a wall that blocks energy from flowing freely. The energy was being trapped and channeled against this barrier, forcing the plasma to run hotter than it otherwise could. At the same time, we turned the most powerful solar telescope ever built toward the sun. High on a volcanic summit in Hawaii, the Inanoye Solar Telescope uses a 4-meter mirror to resolve features on the corona just a few hundred kilometers across. By tuning into the infrared glow of heated iron, the telescope finally saw those twisting Alfvén waves ringing the magnetic field lines back and forth. These magnetic shivers were finally moving from a beautiful theory to a measured reality. In just a few years, two different instruments, one diving through the fire and one staring at it from a mountaintop, produced the physical evidence needed to account for the corona's extreme properties. After 80 years of debate, we can finally ask, which suspect was actually guilty? Was it the microscopic explosions or the magnetic waves? For decades, we treated these as competing ideas, searching for one mechanism to win out, but our data showed they coexist. The probe found the barriers that bottlenecked energy, and the telescope found the waves that transport it. They are different parts of the same system. The corona is heated by a simultaneous symphony of processes. Magnetic field lines snap and burst in nanoflares. Alpha waves travel up those same field lines to shake energy loose, and helicity barriers trap and redirect the flow. This teaches us that the universe rarely relies on a single, isolated mechanism to achieve something this complex. The sun hides energy throughout its tangled magnetic field and releases it through an interconnected orchestra of fire. Understanding how this atmosphere heats is what allows us to understand the solar wind. That million-degree crown is the engine that launches particles out across the entire solar system. These storms of charged particles create the auroras, but they also dictate space weather. They pose a threat to our satellites, our power grids, and our global communication networks. To protect our way of life, we have to understand the engine that drives them. We solved a century-old mystery by the slow, stubborn work of getting closer and looking harder. By building machines daring enough to touch a star, we finally learned how to read the impossible glow of our own familiar sun.